The study of complex behaviors focuses primarily on goal-directed movements which require accomplishing a goal. When looking at the game of darts or pointing motions in general, the variability of the endpoint error between the landing hand and the desired target is the focus of reach. Often, the parameter of interest is the trial-to-trial variability of the error between the desired target and the final position of the hand at the target. This approach makes such movements into discrete epochs, consequently leaving out intermediate connecting movements co-occurring in the continuous flow of our behaviors. We decided to open a new line of research, whereby we study behavior as a continuous flow, including goal-directed segments deliberately aimed at the target and spontaneously co-occurring interconnected segments that make complex behaviors fluid. To that end, we chose a boxing routine including the jab, cross, hook, and uppercut commonly used to train athletes and teach the basics of martial arts. The athlete here is a martial arts expert and competes regularly in kickboxing events. We instructed him to move at various speeds to ask if the goal-directed segments would be affected by the changes in dynamics. Deliberate motion segments were easy to identify since they were aimed at the target, and the spontaneous segments revealed themselves when we studied the full body in motion, rather than just one arm or one hand at a time, as it is traditionally done in motor control. The speed profiles of these complex motions automatically revealed the segments of the full movement. On the other hand, the trajectories of the hand revealed different classes of motor control. Those segments, deliberately aimed at the goal, remained invariant to the changes in speed, while the spontaneously co-occurring segments changed their curvature with the speed of the motion. This figure reveals the deliberate kinematics in black and the spontaneous kinematics in color, red for slow and green for fast. We then decided to take the question a step further and place loads on the arms of the athlete. As he adapted to the loads, the hand trajectories of his deliberate segments remained quite robust. However, as with the speed variations, the trajectories of the spontaneously co-occurring segments changed their curvature and torsion in 3 dimensions. The result from removing the loads from the arms surprised the athlete because he had acquired extremely fast speed, and this after effect of the load adaptation lasted long enough that he used it to surprise his opponent in his next competition. His motions had doubled the speed in ways that he could not have anticipated, and neither did his opponent. The trick had worked. We then decided to apply our automatic motion segmentation criteria to other complex sports and studied the tennis serve. Here is an athlete practicing the serve as we record and plot the trajectories of the hand. The athlete is tossing the ball with the right hand and striking it with the left. We are examining the toss and strike segments of the tennis serve along with the resting segments between trials. It can be seen that automatic decomposition of movement leads into deliberate or goal-directed and spontaneous or uninstructed segments. Then, using the speed profiles, we can automatically identify the deliberate and the spontaneous coexisting segments of the tennis serve, while the athlete is tossing and striking the ball. We seem to have discovered 2 classes of movements in motor control.